So there's this type of number called Fermat numbers, and they're numbers with this form. So 2 to the power of 2 to the power of n, where n is any natural number, plus 1. And if we list them off, they start off when n is 0, all of this is 3. When n is 1, all this is 5. When n is 2, all this is 17. And then it's 257, and then 65,537, etc., etc., etc. Now the thing about these numbers is that if you take whatever previous numbers are on the sequence, multiply them together, and add 2, you end up with the next number. And we can see this using the first three numbers, that 3 times 5 plus 2 equals 17. And this property of being able to make a new number in the sequence by multiplying all the previous numbers in the sequence together and then adding 2 holds for all of these. And that's what we'll prove throughout the course of this proof. The reason why that's significant is that if you have, say, 3 times 5 times 17 plus 2 equaling 257, and if you can make an infinite number of this type of number, and you see that each of them is made by multiplying the previous numbers together and then adding 2, then you have to consider that this new number in its prime factorization, when we factor it out, its factors, its prime factors, can't be the same as these numbers because it's different from multiples of these numbers only by 2, not by these numbers themselves. So it can't be factorized into any of these previous factors. Now it's possible that it could be factorized by 2, but you'll notice that because these are multiples of 2's, each of these numbers with a 1 added, then therefore none of these Fermat numbers is going to be divisible by 2. So for each one of these that you have, it'll be decomposable necessarily into at least one new prime number. And because there's an infinite number of these being decomposable into at least one new prime number is going to mean that there's an infinite number of primes. So the challenge then is to prove that this relationship holds. And I've just pulled the 2 over from this side to here. So it's all the previous terms in the sequence plus 2 equals the next term in the sequence, and I've just pulled the 2 from here to here. So we already implicitly looked at the base case, but I'll just run over it again. On this side we'll have 3 times 5, and then on this side we'll have 17 minus 2. This will be 15, this will be 15, checks out. So then to check if we can use this as a recursion all the way through the sequence, all we need to do is check that this side of the equation is equal to this side of the equation. And we can do that with a little bit of multiplication and with a little bit of substitution of this formula for the nth term of f. So the first thing we'll do is we'll multiply both sides by the nth term, or the nth f. On this side, we're already at the nth minus 1 f. So if we multiply it by the nth f, then this becomes k to 0 to n of f of k. And then on this side, it's the nth f times the nth f minus 2. Now what that means is this minus 2 times this. And I hope I don't run out of space too quickly. I might just have to make a bit more space. We'll see how we go. This is going to be minus 1 and plus 1. And then multiplying these together, we'll have 2n plus 2n, and then plus one of these minus one of these, so 0, and then times minus 1. So this will be 2, and then there's 2 of these, so it's 2 to the power of 1 times 2 to the power of n, and then it's all minus 1. So this is adding these powers together because we're multiplying their bases together. We get 2 to the power of 2, n plus 1 minus 1. About what f of n plus 1 actually is, it'd be 2 to the power of 2 n plus 1 plus 1. So this is actually this minus 2, which means that this whole thing here is f n plus 1 minus 2. So this relation holds in general as well as in the base case, which means that we've proved that each of these Fermat numbers are formed by multiplying all the previous Fermat numbers and then adding 2. And then just recapping, what that means is that there has to be new prime numbers, at least one new prime number, for each of these Fermat numbers, and that therefore, in order to satisfy that demand, there has to be an infinite number of prime numbers in existence.